Welcome back, everyone, and now we're back with another video about ray intersections. We're going to continue on until we reach terrains. So next up is quads, rectangles, squares, whatever you want to call it. It's a 4-point polygon, I guess. All right. Most likely it has to be equal or pretty even, like a rectangle or a square. Can't be just any polygon. So we're going to deal with quads, and we're also going to deal with circles. These shapes are pretty useful when you're, I guess, dealing with certain things, especially like UI. So if you're going to draw your own UI stuff, especially you're going to have like buttons in 3D environment, you can then have that quad take up the shape, because a quad would be easier to do an intersection with than like a bounding box or anything. So when it comes to maybe some items that you want to just click on, it might be very useful to have quads under your tool belt and how to intersect them with an array. Same thing with circles. Buttons can be in circle shapes too. So right now, to draw a circle, I need a quad anyway, so I combine them both together for now. And so there is our quad. So we're going to start looking at some code. I'm going to show you quickly what the circle thing looks like. We did this many videos ago. But yeah, I'm just going to go quickly zip right through it, and you pause the screen if you want to type this all out or just get all this stuff from GitHub. But yeah, just it's pretty much the same rehash of how to make a circle by using the UVs. And there's a material, it's commented. So here's all the code, how to make a circle. The transparency is there. I just don't have it turned on. I'll turn it on up here later on. Use blending is currently off. Also updated the shader load function, which you might want to get that from GitHub as well, which makes this one work, because that was a feature that I couldn't turn on with materials, and now you can. It's a small little minor fix. It'll be in the link below and on the changes for fungi. Since I really don't want to spend too much time talking about minor changes, I just inform you if you guys need it. Get the code from GitHub. Let's see. So now that we look at that, we're going to bring in our shader. Now you can kind of see that we can bring in multiple shaders in whenever we want. And we are creating our quad, passing in our shader, we're moving it to a separate position. And, we have on our camera mouse down, we just grab our points, draw the line, and call our function in quad. So now that we're finally here. So intersection of a quad. It's very similar how to do a triangle. They're very, very similar. Just like with what we've been doing before, you need to determine its plane. So its plane is defined by a direction and a point. So for a quad, we can use its position as its point in space. So that point is where the plane comes into existence. And now we need to determine its direction. And it's pretty obvious the direction here is 0, 0, 1. But in case you don't know how to determine that, especially if you rotate the quad, then its direction is different when you rotate it. So to quickly, easily determine, you have to know what the size of your quad is. Ideally, you probably would make a quad object that stores its dimensions. But if not, like I have a quad that doesn't store the dimensions, it creates it and then kind of the data gets trashed because I don't really need it. But ideally, maybe if you do this a lot, maybe you want to have a quad object that can store its width and height. So the thing is, once you know its width and height, basically this is what these values are. I have to add it to position, because when you're dealing, because we didn't do this with triangles, but with quads, I'm showing you that you need to keep everything in world space. So even though we need to know its plane position and its plane direction, all the points on our quad have to be in world space. So these are all local space values. But since I translate the value up 1 unit in the y direction, that means these are no longer world space. Now they're just local space coordinates. So that's why I'm taking the position, making a copy of its position, and then adding on its local space coordinates. This way, I get the world space coordinates for all 4 corners of the quad. Now, to get the direction of a quad is pretty easy. You just grab 3 consecutive corners. So like for me, I'm going to grab 0, it's right here, 1 here, and 2 here. Do I use 1 as the center? Yeah, I use 1 as the center. So I'm going to use this as the center point of like an angle. So I want to get the unit length from 1 to 0, and not the unit, the vector length. The vector length from 1 to 0, right? And then I want the vector length from 1 to 2. So I want to get the length vector for this angle, right? So that creates 2 points, or 2 lines technically, because those are the 2 edges essentially. Once I have those 2 points, all I have to do is do the edges backwards with a cross apply. So this is edge 0 and this is edge 2, but I'm going to do cross apply of edge 2 to edge 1. If you do it back clockwise, or if you go from let's say 1 to 2 going in this direction, you're going to get a normal that goes in the opposite direction. So it's going to go pointing that way. But the actual forward direction is actually over here. This is the positive side. Crossing this line is the negative side. So we got to do it clockwise. Even though our points are created counterclockwise, to get the correct forward direction, we have to do it clockwise. So we say edge 2 cross edge 1 gives us our normal. So that's what we're doing here. So we, like I said, we're getting these 2 edges, and then we cross apply them backwards. I say counterclockwise, but I think it's actually clockwise because the points are counterclockwise, but the way you get the lines are clockwise, I think. If it doesn't, so yeah. So we're doing that cross apply, and we're going to save it into plane normal, and then we're just going to debug the thing. So we're going to take the plane position, make a copy of the normal, and then add plane position as the second coordinate. And that way, if I do a click, it's probably hard to see, but there is a little gray line. I just changed the color. I think 6 is black on the array list. Refresh. There we go. See, there's the normal. So once we got those 2 points, those 2 edges together, and then cross apply them, we got that normal. Same thing with a triangle. So like I said, if you ever need to get a normal direction, just get an angle type of thing set up, like 2 edges together, and then just cross apply them clockwise, and then you get the forward direction. If you want the backward direction, do it counterclockwise. So now that we have our plane position and we have our normal, comment this out because we don't even need to see the normals. We can then call the function that we did in the first lesson about intersections, how to intersect the plane. So we have that function that already exists, and we'll just, boom, there we go. So there you go, and that's it. So, and this is all the stuff, like I said, we've been doing for triangles in the previous 2 videos. So nothing really new here if you've been following, but if you're new to these lessons, you're hopefully you caught up. So now we're going to go to the really new stuff, to really how to calculate it. So we're going to grab an edge, and then we're going to do a projection onto that edge to determine where the position is. So if I go over here, and let's say I click here. As you can see, I highlighted that edge. So we're creating this edge. So we're going from point 0 to point 1. and determine, and we're going to get its vector length. So we got the vector length and we drew the vector length. From this point, we're going to create another vector length to the point of intersection that's on the plane. Right? So now we have these two edges. You notice everything we do when it comes to intersections, it's creating edges and triangles and figuring out angles. So now what we're going to do is actually, it's called a projection. But the idea is to find the point perpendicular to the edge. So that's what's happening here. I'm creating a perpendicular line. And you just do that by doing an equation of vector A, length of A dot length of B over length of B dot length of B. And pretty much, like I said, here's the equation. And those lines means it's a vector length and not like a vector. So that's, like I said, and this is really how it's implemented. Now, first you got to calculate your vector lengths, and then you do that little equation. You got the dot product of that plus the dot product of that, create your t, and that determines how far in this line you need to be to have that perpendicular line when you have this angle created. Ideally, essentially, you're basically trying to make a perfect triangle, a perfect right angle triangle. So if I click out to here, you see that it's not on the line anymore because it is still being projected at the right at a perpendicular. Because even though I'm highlighting this line, that is the min and maximum bounds of our quad. But these lines are infinite. So that's why it can go up or it can go down. But here's the beauty thing. If it goes past either point, then we know it's not a hit. So the first time it was 0.03, and that's fine. The second time was a negative, and then there was a 1.2. If the t value is not between 0 and 1, then it's a miss. So it's an absolute miss. But like if I do it over here, it's a pass because it is between 0 and 1, but it's on because it's on the other side. Still a miss. So the idea is that when you do this, you have to check at least two axes. So we're going to check the height, and then we have to check the width. And it's the exact same process. You create the edge, right? You determine the edge, and we're going to move. So we did from 0 to 1. Now we're going to do 1 to 2. So we get those two vector lengths, and then we apply the exact same equation of t, and we output, we visualize all that in the same way. So if I go refresh, and now you see the second test is in red, the first test is in blue. So the first test is successful. It's between 0 and 1. Second edge test is outside the edge. It's outside. It's a negative 0.6. So that means it's failed. It's not in it. If I click inside, now it's within those two ranges, and the values indicate that it's half and half, and that's positive. So if you were to test it, you'll test edge 1, and if it's not between 0 and 1, it fails. Then you test edge 2. If it passes, then means it's successful. This point of intersection on the plane also intersects the quad that exists in this point of world space. And that is all to it, really. That's, like I said, it's just projections. And all you have to do is check two sides of a quad. Now, the only thing you have to keep in mind is that, like I said, what I did here is that I took the position and I added its local space so I can get world space. With a quad, you can do a lot of things with 3D space. You can rotate and you can scale. So I think I made a note here that, if you're going to rotate and scale the quad, you need to apply those transformations to these 4 points as well. if you're building something yourself, you just take whatever values you have for rotation and apply it to all these 4 points. If you have a scale value that's not 1, apply scale to it. And same thing with position, just add position. If you're using fungi or you're building something similar where you have a transformation matrix that's created based on the 3 transformations, you can take that transformation matrix and then multiply it by each vector to get its world space vector. So that is the only thing other thing you need to do if you're going to, which most likely you're going to need to rotate and scale quads. So that's the only stipulation you kind of have to do. And I didn't bother. The only thing I did was the translation transform. Like I said, you need to apply rotate and scale if you are doing any of those to your quads. And the same thing goes true for triangles. In the previous lessons, we did just triangles. And I didn't really talk into that because we're busy trying to figure out projection and everything else. But keep in mind, if you're moving things around and rotating things, when you're testing the points in space, they have to be in world space. That is the only thing you need to do. Once they're in world space, then you calculate the normal, its position, and you start doing all the rest of the math, which is pretty easy. And this part can be broken down into a loop, and like you're checking between 0 and 1, and the second time you're checking between 1 and 2. So if you do a loop between 0 and 1, and just do I plus 1 to get the second point. It's really easy. Probably in future videos, I'll quickly add that here. I haven't bothered. It's no point really right now because I don't. At some point, I'm going to probably use a quad or something special for intersections. Like I said, each system is going to be different. You can build it in any ways you want. So hopefully at least you understand the math and you can visually see what is going on here. So this way you can kind of see how it works, how the math handles itself. So if as long as, like I said, if those 2 projections result in a value between 0 and 1, you got intersection working. So now that we got quads working, now how about we start dealing with circles? Circles are just the same, but a lot simpler. So let's add blending. All right. And then we're going to comment out in quads and then comment in circles. So we got in circles. All right. So we refresh and we refresh. Now we got a circle. We got rid of the corners that makes the quad. So here's our circle. Now here's the second part of the video. Intersection follows the same thing. You need its position and you need its normal direction. Not exactly sure how to get the normal position of a circle, but here's the thing. To make a circle, you need a quad. So you can use the quad to actually create the normal. But I didn't bother with this, to be honest. So I just hard-coded 001 because that is the direction it's facing. That's the default direction of any vertex you make, usually. So the same thing. You have those things. You get its position. And then you draw the point of intersection. That nothing's new. And this is what the new part is. Those 2 lines of code plus this if statement. This 3 lines of code determines how you do a disk. So the idea with the disk is, and you might be able to see it this way, and you can see it not in a circle. Since you know the center point, and you know the point of intersection of the plane that this circle resides in, the only thing you have to do is get the vector length between these 2 points. And if these vector lengths are less or greater than the radius of the circle, then it's false. It's not a hit. It's not a hit. Not a hit. I can get very close. Maybe if I can zoom in a little bit. Try to get very close to the circle. Still not a circle. But if I go right in there, in circle, done. And that's really all to it. It's just the length. The length between the center point and the point of intersection, is it less than or equal to the radius of the circle? Now the only thing you'll see that's a little weird here is that I'm not actually using the proper length. It's not the true length between those 2 points. I'm using length squared. Now, why am I using length squared instead of length? Because to get length, you need to do a square root. And square root is one of those math operations that's the slowest for a CPU. If you're doing a one-off thing, it's no big deal. If you're doing like thousands of calculations, a millisecond, not using square roots would help you. It would help things along a lot better. So to calculate length, you have to do a square length basically. I know there's a name of I know the name of what the formula is, but the length is pretty much x1 times x2 plus y1 times y2, whatever, and so on and so forth. And the plus the z. If maybe I should just do it for completion's sake. So z1 times z2. So that is length squared, basically. That's how you get, and then once you have this, you then take that value and do a square root of it, and that gives you the exact length between those 2 points. And you might be like, why am I using a dot notation? Because a dot notation actually follows the exact same formula. I'm passing in the exact same value twice. So instead of me writing out this equation, I can just use the dot product to actually, with a dot product to itself, to actually get its length squared. So ideally, you can just do, math dot square root and surround this, and you get the actual length of those 2 points. So now, since I'm not doing the complete length equation to get the actual length, I'm stopping at length squared. To do a comparison, all you have to do is square your radius. What is the equation? I remember seeing the equation before. It's like this equals length squared. So if I want to get length, you then have to, it'd be easier if I actually had like a tablet and I can draw it. But, if you're going to rewrite the equation and you just want length, then you just take away this square, you bring it onto this side, and you apply it as a square root. So since I'm stopping at the final step of the length equation, I'm not completing it. But here's the thing. If you look at the original equation, this equals length squared. So like I said, all I have to do is take radius squared, and radius squared is radius times radius. So instead of doing a square root, I just do an additional multiplication. The multiplication is faster than the square root. So if you don't need to actually, if you need the length, like the actual number of the length is very important, then do the full equation. If you want to optimize your code a little bit, speed things along, then you can try to do everything in length squared. So if like I said, I know my radius is 0.5, so 0.5 times 0.5 equals 0.25. Why do I know my length is 0.5? It's because my quad is a 1 unit length. So if it's a radius, it's half of 1, which is 0.5. And that's it. So yeah, that's like I said, if you were to add that square root, then you would only need to do length less than or equal to radius. If you're going to keep your square values, just say length squared is less than or equal to length times length. And that's it. And that's everything really. Like I said, this gets the vector length, v length, and then I just do a square length equation on it, which is similar to a dot product. And that is it. Now you can intersect circles as well as quads, even though you need a quad to have a circle. You can actually draw a circle like you draw lines at increments and do like a draw mode of line. You can do that, but you can't fill it in. You just end up making an outline of a circle. But yeah, that's it. So that's it for quads and circles. The next thing we're going to deal with is bounding boxes. I got that done. I'm going to try to see if I can do a video really quick. It's very similar to how quads are done, except that you're going to do 3 different axes. But instead of using vertices, you have to do everything in a single dimension. It's kind of cool how it works. So it's axis aligned bounding boxes will be next. After that, I want to do oriented bounding boxes. That's when we really have to start dealing with rotation and scale and things like that. And spheres, capsules, and I want to try to end it off with terrains, so we can shoot, and not the grid. This is really just this grid is just a plane itself. So I can just do a plane intersection to determine where on this grid I'm clicking on. When I mean terrain, I want a terrain like, you know, there's hills and valleys, and I want to be able to intersect that. So that would be like the last thing of intersection that I want to deal with. I don't really need it right now, but I might as well, if I'm doing all these videos about intersections, I might as well cover that for people who might want to do like a terrain editor. So you need to be able to intersect a terrain so you kind of know where in the terrain, then you can grab the vertices and maybe you can raise the vertices. Like, so with rate to terrain intersections, you can start doing terrain editors. So I would love to do that at some point, but at least if I get that much code written and a video pushed out for it, maybe anyone can start doing a terrain editor too. So yeah, that's about it. All right then. So that's it for now. See you guys in the next video. We'll both be dealing with bounding boxes, which is one of the most primitive and most important things for I guess if you're gonna do game development, because you're gonna especially when it comes to collision, spheres, capsules, and spheres, capsules, and bounding boxes are your bread and butter when it comes to collision. So we're going to deal with ray intersections, and then in some point in the future when we have physics videos, we'll take all this knowledge and then apply it as for collisions. So that you have a quad on quad and a sphere on cube, you know, things like that. So yeah, like and subscribe. See you guys at the next lesson. Sayonara.